All right, so this is baby real analysis problems, and this will be problem 9. So this supplements the baby real analysis YouTube playlist. I think it's called Intro to Real Analysis playlist, but in the videos I call it baby real analysis. It was like a play on the Rudin series where they have Papa Rudin or Baby Rudin, as far as the Baby Rudin textbook being the principles of mathematical analysis, and the Father Rudin textbook being the real and complex analysis textbook. So that's sort of why I'm using the baby name to this. It's an introductory level. In this problem 9, I'm taking from Bartles' Intro to Real Analysis 4th edition textbook. So the last video with problem 8 was Jay Cummings' textbook dealing with sequences. This is more examples of sequences. And so these two examples, 5b and 5d, are going to use the definition of convergence for a sequence to show that these limits are what they are. And then this is example 7, and as far as chapter 3, this is in chapter 3, section 1 in the chapter 3. So this is the example 7 in that exercises, and this is you have a sequence that's equal to 1 over the natural log of ln plus 1 for n is a natural number. And again, we're going to use the definition of convergence to show that it converges to 0. And then part B is going to say use specific values for n that are required to guarantee the convergence, for which epsilon is 1/2, and then epsilon being 1 over 10. And then last, here's example 8 from that section, and this will be proving that this limit equals 0 if and only if the limit of the absolute value of the sequence is also 0. And then give an example to show convergence of a sequence that has the absolute value of the terms does not imply the convergence of the sequence without the absolute value. Okay, so I'm going to go through these fairly quickly. And again, I do sort of a strategy for finding the necessary capital N index. So let's go ahead and get started. So this is 5b, and we're showing this 2n over n plus 1, that sequence converges to 2. Okay, so the definition of convergence as far as the YouTube videos I've been doing. So definition. So we said the sequence an converges to some value a in the reals as the terms get, the indices get infinitely large. So as n goes to infinity, and that's if and only if for all epsilon there exists a capital N in the natural numbers, so that for all little n bigger than capital N, so for the terms with indices little n that are beyond the index of term with beyond the index with term with index capital N, you have the absolute value of an minus a to be less than epsilon. So they were within an epsilon, I guess, radius, you could call it, about the limit point. So that's what it means. Now, the first thing I'm going to do is find the necessary n for this example 5b. So this will be the strategy. This isn't the actual proof. So strategy for finding capital N. So we need the absolute value of our sequence, in this case it's 2n over n plus 1, minus its limit point, or point that it's converging to, which is 2. So the absolute value of 2n over n plus 1 minus 2, we need this to be less than epsilon. And we're going to find the n that makes that work. Well, I'm going to combine the stuff in the absolute value as one fraction. So 2 is 2 over 1. I'm going to multiply it top and bottom by n plus 1. So we have that common denominator. So I'll have 2n, and then when I distribute the minus 2, that makes that minus 2n, and then minus 2. And then all of that's over n plus 1. And so the 2n and minus 2n cancel out, so you have the absolute value of negative 2 over n plus 1. And then that's going to be less than or equal to just positive 2 over n plus 1. And so we're going to be using little n. So little n is bigger than capital N. So then n plus 1, let's see. So then we'd have 2 over little n plus 1 is going to be less than 2 over capital N plus 1. Because we're dividing by the n plus 1 is going to be a smaller number. The capital N plus 1 is a smaller number that we're dividing by than the lowercase n plus 1. And then also n plus 1 is greater than n, so then 1 over n plus 1 is less than 1 over n. And so 2 over n plus 1, that's less than 2 over n. Okay, and then we need this to be less than epsilon. So we need 2 over n to be less than epsilon. So that means if and only if 1 over n is less than epsilon over 2 by multiplying both sides by a half, then taking the reciprocal of both sides, that means capital N is going to be greater than 2 over epsilon. So this is the n that we need. All right, and again, this is all scratch work. Now the proof. So proof, you always start out given epsilon, and then by Archimedean principle or Archimedean property, we can find an n in the natural numbers, capital N, the natural numbers, such that capital N is bigger than 2 over epsilon. So then for all little n bigger than capital N, which is, again, that's bigger than 2 over epsilon, we have the absolute value 2n over n plus 1 minus 2. And we said that was equal to negative 2 over n plus 1. And that's less than or equal to positive 2 over n plus 1. And this is less than 2 over capital N plus 1, since little n is bigger than capital N. And then this is less than 2 over capital N, since 2 over capital N is capital N smaller than n plus capital N plus 1, so you're dividing by a smaller quantity with the 2 over capital N versus the 2 over capital N plus 1. So the number 2 over capital N is bigger. than the number 2 over capital N plus 1. And so we have 2 over capital N, which is the same as saying 2 times 1 over capital N. And then that's going to be less than 2 times, and then 1 over capital N. So if we have capital N bigger than 2 over epsilon, this means 1 over capital N is less than epsilon over 2. So this will be less than 2 times epsilon over 2, which the 2's divide out, and that gives you epsilon. All right, so that is the proof for that one. Okay, so I just zoomed out so you could see the whole proof. All right, so now the next example is as far as the Bartle textbook, it's exercise 5D in chapter 3, section 1. So example 5D. So we're showing that the limit of n squared minus 1 over 2n squared plus 3 is equal to 1/2. Okay, so this is the problem. So now, again, I'm going to find the necessary index capital N. So strategy for finding N. All right, so we need the absolute value of our sequence n squared minus 1 over 2n squared plus 3 minus the value in which it converges to, so saying converges to 1/2, to be less than epsilon. So again, I'm going to combine this into a single fraction like in the previous problem. And let's see. So the n squared minus 1 over 2n squared plus 3, I'm going to multiply that top and bottom by 2. And then the 1/2, I'm going to multiply that top and bottom by 2n squared plus 3. All right, so what does that give us? That's going to be equivalent to, so we have 2 times n squared minus 1. I'll go ahead and distribute the 2. That makes that 2n squared minus 2. And then we have minus 1. Then I'm multiplying the both of those, so that makes that minus 2n squared, and then minus 3. And all of that is over 2 times 2n squared plus 3. All right, so the 2n squared minus 2n squared cancel out, and then we have minus 2, then minus 3 makes minus 5. So that's going to equal minus 5 over 2 times 2n squared plus 3. And that's less than or equal to positive 5 over 2 times 2n squared plus 3. And again, we need this to be less than epsilon. All right, so to make it a little bit easier, since 2 times 2n squared plus 3 is just greater than 2n squared plus 3, then taking the reciprocal, so we have 1 over 2 times 2n squared plus 3 is less than 1 over 2n squared plus 3. All right, so 5 over 2 times 2n squared plus 3 is going to be less than just doing 5 over 2n squared plus 3. So it's dividing by a smaller number. But then 2n squared plus 3 is greater than 2n squared, so taking the reciprocal of that, 1 over 2n squared plus 3 is less than 1 over 2n squared. So this would be less than 5 over 2n squared. And squaring a natural number makes it bigger than that natural number. So 2n squared is greater than 2 times n. So then 1 over 2n squared is less than 1 over 2n. So 5 over 2n squared is going to be less than 5 over 2n. Okay, and then we know n is bigger than capital N. So then that tells us essentially 5 over 2 times little n is going to be less than 5 over 2 times capital N, because n greater than capital N means the reciprocal of both sides flips the inequality. So that's if and only if. Okay, so then we have this string of inequalities, and we need this to be less than epsilon. So multiplying both sides by 2/5, that gives us 1 over capital N, needs to be less than 2 epsilon over 5. And then taking the reciprocal, then n needs to be greater than 5 over 2 epsilon. So that's the index that we're going to use. So now the actual proof. So given any real number epsilon greater than 0, by Archimedean principle, we can find n, capital N, such that capital N is greater than 5 over 2 epsilon. So then for all little n bigger than capital N, all right, and when that's greater than 5 over 2 epsilon, we have the absolute value of n squared minus 1 over 2n squared plus 3 minus 1/2. And we did some algebra, and that gave us to be equal to negative 5 over 2 times 2n squared plus 3. And we said that's less than or equal to positive 5 over 2 times 2n squared plus 3. All right, and then that itself is less than just 5 over 2n squared plus 3. And then 2n squared plus 3, that's greater than 2n squared. So we said that when we have this 5 over 2n squared plus 3, that's less than 5 over 2n squared. Since that's dividing by a smaller quantity, makes 5 over 2n squared bigger number. But then squaring a number makes that number bigger, so dividing by just that number, so dividing by just n, makes it to be a smaller denominator that you're dividing by. So instead of, so we can say 5 over 2n squared is less than 5 over 2n. And we know n is bigger than capital N, so 5 over 2 times little n is going to be less than 5 over 2 times capital N in the denominator. But then 5 over 2 times capital N, that's the same thing as 5 halves times 1 over capital N. And we know that since capital N is bigger than 5 over 2 epsilon, that means, in other words, 1 over capital N is less than 2 epsilon over 5. So then we could say that 5 over 2 times capital N in the denominator, which is the same thing as 5 halves times 1 over capital N, that's going to be less than 5 halves times, and then we had 1 over capital N, which that itself was less than 2 epsilon over 5. So then that way the 5's divide out, and then the 2's divide out, and that just gives us epsilon. All right, so that's how I did the proof. So I zoomed out just to show it, and I did have a lot of strings of inequalities. So I could have condensed it and maybe just said, 5 over 2n squared plus 3 is eventually just less than 5 over 2n. And that's less than 5 over 2 times capital N. And then just eventually just say that's less than epsilon if I wanted to just make it a little bit shorter. Okay, so that's that example. And I think I will end it there and do a part 2 to this example. So this problem set I was saying was problem 9. And it was like 4 problems taken from Bartles' Intro to Real Analysis, Chapter 3, Section 1. And so I've done this example, and I've done this example. So the next video, I'll do this one. I think this video is already be long enough.